Good evening, everyone. Welcome to NPTEL tutorial session for the course Essentials of Oxidation, Reduction, and Carbon-Carbon Bond Formation Application in Organic Synthesis, taken by Professor Yashwant D. Vankar, retired from Chemistry Department, IIT Kanpur. And my name is Sri Lakshmi S. I'm a PhD scholar in IIT Bombay from the Department of Chemistry. So, in the previous tutorial session, we have been discussing different weeks lecture contents, and we have solved the assignment questions as well as several other questions related to the topics taken in the lecture. So far we have discussed week 1 lecture contents and week 2 lecture contents. Also, we have solved week 0 assignment questions, week 1 and week 2 assignment questions. So in the last session, we have also started the week 3 lecture content discussion, but then moved into we then moved into the week 1 and week 2 assignment question solving session. So today we will be starting with the week 3 lecture content first, then we will move ahead with the week 3 assignment question, followed by week 4 tutorial session. Okay, so in the last tutorial session, we have already discussed about this week 3 lecture content that was about iodoxybenzoic acid, how it works, what is its mechanism of action, then different applications like in oxidation, then in diol cleavage for the conversion of alcohols to enones and its mechanism. So yeah, so about IBX, we have finished the discussion in the last session. So today we will first discuss this Provost reaction and its modification. So Provost reactions are basically silver-based oxidation reactions where we convert alkene into diol. So as we can see here we have an alkene and we are converting that into a diol. So that is Provost reaction, and what we are using here is uh, silver benzoate, some silver salt we are using, in the presence of iodine and benzene. So what is forming first is a dibenzoate. So this alkene will form a dibenzoate, like both the carbons which are forming this alkene will be converted first into a dibenzoate, and which upon hydrolysis using a base will give the corresponding diol. So this is the Prevost reaction. Alkene is converted into this diol by using a silver salt. Now we will see the mechanism of this reaction. So what is happening first? Firstly, here we are using iodine. So this double bond will attack over that iodine, and this it will be like this double bond will attack over iodine. We know I2 means I plus and I minus. So the double bond will be attacking over I plus, and this I minus will be coordinated to the silver cation. So we will be getting this corresponding iodonium ion with the positive charge on iodine. So three-membered ring with a positive charge on iodine is called iodonium ion, and this is the counter ion. So whatever silver salt we are using, it is having a positive part, that is silver, and this negative part, that is the benzoate. So this iodonium ion will be stabilized by the counter anion, that is this benzoate. So then what is happening, this iodonium ion will be opened by this negative charge of this benzoate. So this negative charge will attack over this one carbon, and this bond will open, which will result in this intermediate. So one position we will be getting this benzoate, and in the other position we will be getting iodine, which will be coordinated with the silver. Then what is happening in the next step is this oxygen lone pairs will attack over the other carbon, and this group will eliminate. So silver iodide is a stable salt, so it will eliminate when this oxygen lone pairs will attack over this carbon. So that will result in the formation of this oxonium ion, which is which is having a positive charge on oxygen. So this is another intermediate. Then again, what will happen? The next benzoate anion will attack over the other carbon. So this benzoate anion attacking over the other carbon, this bond is opening, which will result in the formation of a dibenzoate, which is the intermediate which we shown here. So firstly, iodonium ion formation, then iodonium ion will be opened by benzoate. That benzoate will form this kind of a five-membered intermediate. Then other benzoate will attack over the other carbon, and it will open to form this dibenzoate. Then simple basic hydrolysis will remove both these esters. So ester hydrolysis is happening, and we will be getting the diol. So as we can see here, we are getting trans diol. This both the hydroxyl group are in the opposite side. So why it is so? Because this where this five membered ring is forming, the other benzoate group will be attacking from the opposite side of this five membered ring. So here we have shown this five membered ring below, so the other benzoate will be attacking on this carbon from the above face. So one benzoate will be above and one benzoate will be below. So the resulting diol will also be trans. So this is the mechanism of Prevost reaction, conversion of alkene into diol by using silver salt iodine followed by hydrolysis. Is it clear? Okay, I will move ahead. So one problem with this reaction is that this silver salts are quite expensive. That is one problem with this reaction. Otherwise, this is a very like straightforward way for the conversion of alkene into diol. Mostly we will be getting trans diol in almost all the cases. So there is a modification to this Prevost reaction. If water is present in the reaction medium, or if we are using water as a reagent in this reaction, instead of forming the trans diol, it will be forming cis diol or syn diol. So that modification we call was done by Woodward, and we call it as Woodward's modification of Prevost reaction. So this is the Woodward's modification of Prevost reaction. So here, instead of forming this, yeah, dibenzoate, we will be getting this kind of an intermediate. So as we can see in this intermediate, this hydroxyl group is here, and one benzoate group is here. Then basic hydrolysis of this benzoate group will be giving alcohol here, which will be giving this cis diol. So what is happening here? Previously in the mechanism we have seen this intermediate. So in Prevost reaction, what will happen? This intermediate will be attacked by a benzoate anion from the opposite side, so it will give the transdiol. But in the case of Woodward modification, if water is present in the reaction medium, that water will attack over this center, and that will form this kind of an intermediate. So instead of benzoate ion going and attacking at this carbon, water will attack on this positive charged carbon, which will give this intermediate. Then this bond will shift over here and this will open to form this particular intermediate, and then hydrolysis of this ester group will give the cis diol. So this is Woodward modification. So both are the same reactions. Alkenes can be converted into diols. In one case, if water is absent, only silver salt iodine we are using, followed by hydrolysis, we will be getting transdiol. But if water is there in the reaction medium, instead of the second benzoate attack, water molecule will be attacking and we will be getting the cis diol, which is known as the Woodward modification of Prevost reaction. So here another thing we have to we have to know is that the facial selectivity of this Prevost reaction or Woodward reaction will be opposite to that of osmium tetroxide. So we know that osmium tetroxide is also used for the same reaction, that is conversion of alkene into diol. Diol mostly it will be cis diol, but here we can see this is the compound. So if we are using osmium tetroxide, we are getting this diol where both of this are alpha. But if we are using this Woodward condition, here also we are getting cis diol, but both of this are beta. So that is because the facial selectivity is opposite to that of osmium tetroxide. So what will happen in the Woodward condition? Firstly, iodonium ion is forming. So iodonium ion will be forming from the opposite side of this methyl group. Due to steric hindrance, the iodonium ion formation will take place from the opposite side of this methyl group. Here methyl is above, so iodonium ion will be forming. This alkene will attack the iodine from the below phase. So iodonium ion will be forming in the below phase. Then in the next step, the benzoate or the ester group will be attacking from the opposite phase of this iodonium ion. So firstly, the steric hindrance will be created by this methyl group. So iodonium ion formation will take place in the opposite phase. Then again, next attack will be opposite to that of the, it is like an SN2 attack. So this will attack. So this will be attacking from the opposite phase of this iodonium ion. So this OAC group will be above. Then the next OAC group will be also attacking from no, here water is there. So both this hydroxyl group will be on the same side, but we can see the facial selectivity is same as that of the methyl group. That is because here first iodonium ion is forming, then a second attack is taking place. But in the case of osmium tetroxide, what is happening? This intermediate is forming. So this osmium, like this double bond will attack over the oxygen of osmium from the face opposite to that of this methyl group. So this will be forming below, same as that of this intermediate. But in this case, a second attack was there which was opposite to this selectivity, so it will be giving this diol. But in this case, only this cleavage is happening, it is not affecting the stereo centers after this. So we will be getting cis diol, but with the opposite stereochemistry of this methyl group. So just remember that the facial selectivity of this Woodward condition is opposite to that of osmium tetroxide, although both will be giving cis diols. So that is Woodward reaction, Provost reaction, and its facial selectivity. Facial selectivity difference between osmium tetroxide and this silver salt. Yeah, as I said, there are some disadvantages for this reaction. First one is that this requires 2 moles of silver salt and 1 mole of iodine. Both are expensive. Silver is especially more expensive, so this is generally an expensive protocol. So these are the modifications to for this reaction, where instead of using 2 moles of silver salt, if we are using this phenyl diacetate 1 mole equivalent and lithium bromide catalytic amount, what will be forming? This phenyl iodide will form, lithium acetate will form, and it will liberate this bromine gas. So that bromine gas can be used to form bromonium ion with this alkene. So this will give, so instead of the iodonium ion previously we got, this time we will be getting this bromonium ion. Then the same condition like acetic acid, if we are using acetic acid, will open this bromonium ion to form this intermediate. Then next acetate will attack over this position, and mechanism is same, so we will be getting antidiol, and if water is there, syndiol is forming. So this is a modification to the Provost and Woodward condition where we don't have to use expensive silver and iodine. Instead, we can use phenyl diacetate, that is PIDA, phenyl iododiacetate, and catalytic amount of LIBR. So that will in situ generate bromine. Bromine, that bromine can be used to form bromonium ion on the alkene, and then the mechanism, same mechanism as that of the Provost reaction, will follow to give antidiol, and if water is there we will be getting syndiol. So this is a modification of that reaction. If you have any doubts you can ask regarding this topic. Now we will move on to Fettison's reagent. So before that, if you have any doubts you can ask. Okay, then we will move ahead with Fettison's reagent. So Fettison's reagent is used for the selective oxidation of secondary alcohol and allylic alcohol. And what is this Fettison's reagent? It is a mixture of silver carbonate in silicate. So yeah, Fettison's oxidation involves oxidation of primary and secondary alcohol utilizing the compound silver carbonate, which is adsorbed onto the surface of silicate. So silicate is basically a form of silica. So that different size of silica we will be getting. So silicate will be in more powdered form of silica, which is from the natural source. So the first time this Fettison's reagent was used by Marcel Fettison in 1968, and one advantage of this reagent is that it is a very mild reagent. If in our substrate, if we have acid sensitive or basic sensitive compounds or groups, we cannot use many oxidizing agents. For example, if we do swan oxidation and also swan oxidation have oxalyl chloride we have to use, so that is an acid. So if any acid sensitive group is there in the reaction medium or in our substrate, it can get affected. So compared to that, this Fettison's reagent is a very mild reagent. We can use it both for acid as well as base sensitive compounds. Then another application is that it can be used for the conversion of lactols to obtain lactone from diols. We will see that in the example. Then the reaction is inhibited significantly by polar groups within the reaction system and also by steric hindrance of alpha hydrogen of the alcohol. Yeah, so it is a mild reagent. So steric hindrance, and if any other polar groups are present in the reaction system, that can hinder this reaction a little bit. So we will see how is it working. So here we can see we have an allylic alcohol here that is converted into this ketone. So we will be getting alpha beta unsaturated ketone. Here also this alcohol is there. So that is getting converted into this is primary alcohol, so that is converted into corresponding aldehyde. Here we have this diol. So as we said, diol will be converted into first lactol, and that lactol again will be converted into lactone by using the silver carbonate and silicate. Again same here, diol, so it will be converted into lactol and then lactone by this Fettison's reagent. So here we can see in this substrate there are two hydroxyl group, this hydroxyl group as well as this hydroxyl group. But this hydroxyl group is sterically more hindered due to compared to this hydroxyl group because of the presence of these two methyl groups adjacent to this hydroxyl group. So what will happen if we are controlling the equivalence of the silver carbonate and silicate? It will be going and oxidizing firstly this one only, which is more free, and this will be unaffected. So we will be getting this one. So that is what we said about steric factors. Sterically less hindered alcohols will be oxidized. So here also we can see this alcohol is more free compared to this one because of the presence of this methyl junction methyl group, and moreover this is allylic alcohol, so that will be more reactive, and therefore we will be getting this alpha beta unsaturated ketone, and this secondary alcohol will be remaining intact. Then if we see these two compounds, so what is the difference? Everything else is same, only here the hydroxyl group is below, here the hydroxyl group is above. So here it is given this is extremely unreactive, this get oxidized easily. Why? Because if we consider the chair form of both of this can be drawn like this, where methyl, this methyl, 3 methyl are above, mm, and this hydroxyl is below. On this 2 methyls are above, and this hydroxyl is also above. So one criteria for the oxidation of this Fettison's oxidation of alcohols by this Fettison's reagent is that the alpha equatorial hydrogen, like alpha hydrogen, should be easily accessible. So here as we can see, this hydrogen is axial, but this hydrogen is equatorial, and abstracting this hydrogen is very difficult because of the steric hindrance from this methyl group, but this is more free as compared to this. That's why this one will be getting oxidized faster than this one. So this is getting oxidized faster than this one with hydroxyl group below. Same like here also, here we have like OH alpha, OH axial and hydrogen equatorial, here hydrogen equatorial and hydrogen axial and OH equatorial. So this will be oxidized 25 times faster. That is because this equatorial hydrogen will be, mm, this I need to check why it is like this. If you have any idea why this is so, you can tell. They have given like this is more accessible. Okay, this I will look into it and I will tell this in the next class, the exact reason for this one. Okay, so then here what is happening? This silver carbonate and silicate is oxidizing this diol. So as we said, if there is a diol in the system, it can be converted into corresponding lactol and then lactone by the silver carbonate and silicate. Same reaction is happening in this case also. Now we will see the mechanism of reaction. So what is happening here? Here step by step it is giving. First step is the reversible chemisoption of this alcohol on the surface of oxidizing agent with the electrons of oxygen forming a bond with silver plus ion. So this electrons of our alcohol will form a bond with this positive charge silver ion. So this is the Fettison's reagent, silver Ag2 and CO3. CO3 2 minus and Ag2 plus. So firstly this alcohol will attack over this silver and it will form this kind of intermediate. That is the first step. Then oxidation of CH bond occurs. So the HCOH group is coplanar and perpendicular to the Ag2CO3 silide surface. So then oxidation is happening. Oxidation will happen. How we will see, this bond is breaking and this bond is breaking. So it is happening through a radical pathway, we can tell. So this bond will break and this here it will form like, so we have here oxygen is there, here Ag is there, positive charge. hydrogen, hydrogen. So this bond is breaking and this bond is breaking radically. So what will happen? Radical will form here, another radical will form here, radical will form here, and at the center also. Then what will happen? These two radicals will combine and form this compound. So silver metal will be released and this other intermediate will be as such, and we will be getting this intermediate. Then what will happen? If proton loss from this position will give the oxidized product, and this will be the byproduct. So how this silver plus is converted into the silver metal, whatever hydrogen is leaving, that will give the electron and this will be converted into the silver metal. And this byproduct then will be converted into water molecule and CO2, and whatever silver we will be getting back. So this is the mechanism. So this is like not the chemical representation, we can say this is a possible mechanism because we are using silite. So basically this whole alcohol will be adsorbed on the surface of the silite, then this kind of action is taking place. So the suggested mechanism is through a radical pathway rather than an ionic pathway. Firstly, oxygen lone pairs will attack over the silver, forming this intermediate. Then homolytic cleavage of these two bonds will result in the formation of this. Then a proton loss will give the oxidized compound. So, considered irreversible homolytic shift of electrons to generate reduced silver cation, H plus ion, and protonated carbonyl group. Then collapsed products with CO3 minus ion acting as H plus ion acceptor to form carbonic acid that then collapse to water molecule and carbon dioxide. So this is a more elaborate mechanism. I'm not going into detail. It is same only. So firstly, this will be adsorbed. Like this is silite surface where the silver carbonate get absorbed. So firstly, this oxygen or alcohol moiety will bind on that. Then it will form this kind of intermediate. This will go and forming radical over the center. So that will form this double bond over here and resulting in the oxidized product. Ag plus ions are adsorbed at the silver surface. Yeah, so this is just a pictorial representation. So how this is acting on that surface. So I think chemically the other mechanism would be more easier to understand. Yeah. So one advantage of this Fettison's reagent is that usually we know that if we compare primary and secondary alcohols will be more reactive towards almost all the oxidizing agent which we have seen so far. But only with the Fettison's reagent, secondary alcohols will be oxidized more faster than primary alcohols. Primary and secondary alcohols are readily oxidized to the corresponding aldehydes and ketones under mild and neutral condition, but primary alcohols are oxidized more slowly than the secondary alcohol. So if you see here, in this compound we have both this primary alcohol as well as the secondary alcohol, but the product is primary is remaining as such and secondary alcohol is oxidized to the corresponding ketone. Then as we said earlier, it can be used for acid and base sensitive alcohol. One drawback is if polar groups are there or steric hindrance is there, that can decrease the rate of the reaction. Then another factor which controls this rate of this reaction is solvent, whether we are using a polar solvent or non-polar solvent. Usually polar solvents like acetone, ethyl acetate slows down the reaction. Like non-polar solvents or relatively less polar solvent increases the rate of the reaction. So in whichever examples we have seen benzene as the solvent. So benzene is routinely used, but when solvents less polar than benzene such as heptane are used, there is rate acceleration. So, for Fettison's reagent or for Fettison's reagent mediated oxidation, solvent should be considered. But one factor is that solvent should be considered that in such a way that rate of the reaction should not be affected, as well as it should be the substrate or the alcohol should be soluble in that solvent, because mostly alcohols are polar in nature, so its solubility with the non-polar solvents will be less. So careful choice of the solvent is very important in the case of doing Fettison's reagent. It should compound should be soluble, but it should not be very polar solvents also. So some other solvents which are used are toluene, hydrocarbons, and acetone. Then DCM and dichloromethane and chloroform are used as solvent for allylic and benzylic alcohol. So choice of solvents are very important. Then, as we said, the type of alcohol also controls the rate of the reaction. Primary, secondary, allylic. So allylic and secondary will be considered more fastly reactive than primary alcohols. And another advantage of this reaction is that since it is a very mild reagent, if two secondary alcohols are present in the same substrate, we can like this is a symmetric substrate also. So if two alcohols are present in the same substrate, we can selectively oxidize one alcohol in the presence of another one. So here we are getting the symmetric diols, but only mono oxidation is happening, and we are getting this product. So that is due to the mildness of Fettison's reagent. Then if this kind of system is there in the presence of Collins reagent, PCC, PDC, an oxidative breakage of this carbon carbon bond can take place. If we are using PCC, PDC, or Collins reagent, get we will be getting here just ketone we will be getting. But in the case of this John's Moffat oxidation, they were getting complex mixtures with this oxidation of the substrate, and Corichem oxidation, there was no reaction, only starting material was remaining. But in the case of using Fettison's reagent, what they got was only this alcohol reacted, and this remain untouched. Of course, it is tertiary, but rather than getting the carbon carbon bond cleavage product which they got with other reagents, here they could oxidize this hydroxyl group without affecting or without cleaving this carbon carbon bond. So just to indicate that this reaction is under mild condition, this is very suitable for doing such transformations where other reagents can give mixture of products. So, as we can see in this example, here is a dialkoxyalkene group here, which is a very sensitive group. So, if we are using any pyridinium or pyridine based or chromium based reagent, usually we will see decomposition of this starting material because of the because it will be mostly affecting this group. This group is very sensitive and very labile group. But if we use Fettison's reagent, this alcohol can be selectively oxidized without affecting this one. So these are some examples to show that this reagent is very mild and we can use it for controlling the reactivity of the particular alcohol which we need to get oxidized without affecting any other group. Then in the next lecture we have seen this ruthenium tetroxide and ruthenium chloride NaO for mediated oxidation. So here what is happening? This So basically the reaction is like this alkene will be converted into diol, and then that carbon carbon bond cleavage will take place to give the oxidized product. So we will see the detailed mechanism. So this is a powerful oxidant introduced Okay. So this is a powerful oxidant introduced by Carl Gerasi in 1953, and this involves oxygenation and hydrogen abstraction. It's comparable. The mechanism is comparable with osmium tetroxide in the terms of olefin dihydroxylation. That's why I told first step will be the conversion of alkene into the corresponding diol, then carbon-carbon bond cleavage to give ketones, aldehydes, or acids. Okay. So this is very reactive reagent. So this ruthenium tetroxide. So even at room temperature, this reaction can go. Then mostly the solvents such as carbon tetrachloride or dichloromethane are used because if we use benzene or pyridine, it can react with this ruthenium tetroxide. So such solvents are not preferred. Then if we use NaO4 with this ruthenium tetroxide, it can improve the yield of the reaction. Then another drawback of this reaction is yields are not always consistent. Sometimes this reaction give lower yield, and this ruthenium tetroxide is very toxic, volatile, and explosive. So what can be done is using catalytic amount of ruthenium tetroxide or using ruthenium chloride or ruthenium dioxide in catalytic amount along with NaO4, HiO4 or NaOCl as a co-oxidant. So in that case, we don't have to use this ruthenium tetroxide, which is very toxic in equivalence. We can control the amount if we use a co-oxidant like this sodium metaperidite. So what will happen in such cases that we know that ruthenium tetroxide will be soluble in the organic solvents which we are using. So once it is consumed by the reaction, the byproduct will be ruthenium dioxide. So this is the organic phase. Firstly, our substrate S is there. So ruthenium tetroxide will oxidize that S into S double bond O. So ruthenium tetroxide will be converted into ruthenium oxide. So ruthenium oxide is soluble in water. So what will happen from this aqueous phase? This tetroxide will be oxidized back into ruthenium tetroxide by the co-oxidant which we are using, which can be that sodium metaperidite or periodic acid, whichever co-oxidant we will use. So that will oxidize back ruthenium dioxide into ruthenium tetroxide. So we have to use more equivalence of the co-oxidant and lesser equivalence of this ruthenium tetroxide because it will be regenerated in the reaction medium. Then this, as I said, instead of this ruthenium tetroxide, more cheaper ruthenium dioxide or ruthenium chloride can also be used in for this reaction. Yeah, as I said, yields are not always consistent for this reaction. Sometimes reactions are very slow and incomplete. Then this sometimes sluggish reactions, that is a lot of products are formed, or sometimes this ruthenium catalyst is not activated properly, so that time reaction will not work. So that are some drawbacks associated with this ruthenium tetroxide mediated oxidation. And here also this solvent will play an important role. If we are using this acetonitrile as a solvent, we will be getting this carboxylic acid. So here in general case, we will be getting ruthenium trichloride NaO4, we will be getting this alkene which was remaining unreacted, that is same starting material. Then this product, that is only 17 percentage. Then if we are adding acetonitrile, the oxidation is going further and complete conversion was there. 88 percentage of the completely oxidized product, that is whatever ketone is forming, that again got oxidized, and we are getting this carboxylic acid in 88 percentage of field. So addition of acetonitrile can accelerate the reaction and activate the catalyst. And in some cases, if ruthenium like ozone or osmium tetroxide or KMnO4 cannot cleave this alkene, that time ruthenium tetroxide can be used, which is more powerful oxidant than this ozone, osmium tetroxide or KMnO4. So the reaction will be same. Firstly, diol will form, then this carbon-carbon bond cleavage will take place to form this diketone. Yeah. Then another example is the conversion of this primary alcohol into this carboxylic acid using the same reagent. Then it is a non-selective oxidant, that is controlling the reaction with this ruthenium tetroxide. As we saw in the case of Edison's reagent, we can keep the control over that reaction. If we need only one alcohol to get oxidized, it will stop at that stage. But this is very reactive reagent, so it is non-selective. It reacts with multiple bonds, 1 2 diols, aromatic rings, ethers, and almost everything. So here also we can see directly this both will be oxidized to, firstly this is ketone and this is aldehyde, then this will break and over oxidation will take place, and we will be ending up with carboxylic acid in most of the cases, especially if we are using acetonitrile in the reaction medium. Then there are some more examples where this hydroxyl group is getting oxidized into the corresponding carboxylic acid. Then here, yeah, here we can see if we are controlling the time of the reaction, we can stop the reaction at diol stage before this carbon carbon bond getting cleaved and converting into this diketo compound or dialdehyde compound. We can stop the reaction at this diol stage if it is kept for shorter time. Then this is the mechanism of this reaction. Like, mechanism of the reaction in the sense, firstly this alcohol which is primary will be oxidized into corresponding aldehyde. Then how that aldehyde is converted into corresponding carboxylic acid. So ruthenium tetroxide will this yeah, oxygen lone pair will attack over here and this will become OH to form this intermediate, and then this cleavage will happen, ReO3 will be regenerated and we will be getting carboxylic acid. So controlling at the aldehyde stage is difficult. Only if we are keeping it shorter time, maybe we can get the aldehyde or diol. Otherwise, it will be almost always going to the complete oxidized, over oxidized product. Next, one of the major application of this ruthenium mediated oxidation is that a phenyl ring can be cleaved into this carboxylic acid. So because we know phenyl rings are having their aromatic compounds benzene ring, so it is having double bonds, so that double bonds will be cleaved by this powerful oxidant ruthenium tetroxide, and this in place of this phenyl ring we will be getting a carboxylic acid. So here also same reaction, first diol, then that cleavage, aldehyde will form, that is oxidized into carboxylic acid. Then, if nitrogen ligands are used along with this ruthenium chloride and NaIO4, we will be ending up with epoxides. So, here what is happening? This nitrogen ligands will coordinate with this ruthenium and it will form this kind of an intermediate. So, oxygen will attack over this alkene, this will attack over this ruthenium and form this particular intermediate. Then, what will happen? This will attack over here, this bond will break, and we will end up with this epoxidation product. So if nitrogen ligands are used, we can get this epoxidation products. Then another important reaction is oxidation of ethers. Instead of alcohols, it can oxidize ethers into the corresponding ester or lactone. So here also this is an ether, cyclic ether. So that is oxidized into corresponding lactone. Here also this is an ether moiety. Here it is converting into lactone. Same with this also. Even if it is sterically hindered, it is oxidizing this ether into this corresponding lactone. So how it is happening? Firstly, this ruthenium will coordinate with this oxygen, so it will form this particular intermediate. Then what will happen, this O minus will take this proton, so that will form, this O minus will take this proton, this bond will shift over here and this will break, so that will form this particular intermediate. Then what will happen again, this O minus will go and attack over this carbon, and this will stabilize the positive charge on nitrogen, forming this intermediate. Then this cleavage is happening, like This oxygen lone pair will take this proton, and this bond will shift over here, and this will break, and this will become OH, forming this one and this intermediate, which upon water removal we will be getting RuO2. So we have started with an ether moiety and we are ending up with this lactone. So this is very important application of this ruthenium tetroxide. We have so far seen only the oxidation of alcohols into corresponding oxidized product, but here in this case, even ethers can be oxidized into corresponding esters or lactones by using ruthenium tetroxide. Another modified reagent which is a ruthenium based oxidizing reagent is tetra n propyl ammonium perruthenate. We will call it as TPAP. So this is the structure. Tetra n propyl ammonium ion is there, and then ruthenate is also there. So for this reagent, this NMO is used as a co-oxidant. NMO can be used as co-oxidant, or this NaOCl or oxygen can be used as a co-oxidant. This one advantage is that it is milder as compared to this ruthenium tetroxide due to the large counter ion. So due to the presence of this large counter ion, its reactivity is quite slow, or it is very less reactive as compared to the ruthenium tetroxide. Because in the other case we have seen every case we are ending up with the over oxidized product like carboxylic acid or carbon carbon bond cleavage. So here oxidation of primary alcohols to aldehyde is possible. We can stop the oxidation at the aldehyde stage. And if molecular sieves are used in the reaction medium which will absorb the water, we can recover this catalyst as well. So this is the mechanism of this TPAP based oxidation. So this is our reagent, that is TPAP. So what will happen first? Alcohol. This oxygen will attack over this ruthenium and this will shift over here. So this will be the product. This will be the intermediate. Then what will happen? This O minus will take this proton. This bond will come over here and this will break. This will go here and we will be getting our oxidized product and this intermediate. So then this intermediate will be oxidized back into the active reagent by using this co-catalyst or co-oxidant, which is n-methyl morpholine n oxide in this case, or we can use NaOCl or oxygen is enough to oxidize this into this active reagent. So a catalytic amount of this TPAP is enough, and stoichiometric amount of co-oxidant is enough to carry out this reaction, and we can stop the reaction at the desired stage without undergoing over oxidation. Then we will see some examples. So here this alcohol, primary alcohol it is getting oxidized into the corresponding aldehyde, and over oxidation is not taking place, and we are getting uh, the oxidation is stopping at the aldehydic stage. Then here this primary alcohol is converting into this aldehyde. Here also same, alcohol into aldehyde. Here also primary alcohol is converting into aldehyde, and here we can see other groups are not affected. This protecting groups or this epoxides, the CB group, which is also protecting groups, these are unaffected under this condition. And here we can see under Swan oxidation condition, the yield was 12 percentage only, but under the CPAP NMO condition, 78 percentage yield of this product was observed. So, as we said, many protecting groups are stable at this condition, like trimethyl, silyl, ethoxymethyl, mom group, methyl, ethoxymethyl, trityl, silyl, benzyl, PMB, THP, acetate, benzoate. These protecting groups are all stable. Then, if enones are there, double bonds, epoxides, halides, all these are stable under this condition. We know that in the case of ruthenium tetroxide, if a double bond was there, that will be converted into diol, and then carbon carbon bond cleavage will take place to give the corresponding acids in the case of ruthenium tetroxide. But here double bonds are also unaffected. I think that was about the week 3 lecture contents which were pending from the last class discussion. Now, before going to week 4 lecture contents, maybe we will discuss some questions. This we have already solved, this week 1 assignment. I hope there is no doubt in whatever I told till this time and about this questions also. Week 2. So this is the week 4 lecture content. So before going to that, we will try to solve week 3 assignment questions. Okay, I have not given animations. Yeah. Okay, so the first question is the major products that can form in the following reaction is or are. So this particular alkene is treated with this selenium dioxide in butanol, DCM at room temperature, which will be the major product here out of the four options given. Okay, that was week 2 assignment question that we already discussed in last class, week 1 and week 2 assignment. So this is the first question of week 3 assignment. In the IBX mediated oxidation of secondary alcohols, an increase in steric hindrance on the substrate alcohol causes increase in rate, decrease in rate, no change on the rate, considerable decrease in the yield of oxidized product. Can any of you answer this? Okay, so here, as we said in the starting of this today's session, steric hindrance is one of the reason which will increase the free energy of the intermediate. So, according to the like mechanism of this reaction, steric hindrance will cause increase in the rate of the reaction. So the reason is given here as per the mechanism discussed, which we see in the beginning of today's class. The twist required for oxidation occurs, and then oxidation is accompanied by loss in energy of the system, and subsequently the rate increases. So IBX is one such oxidizing reagent where steric hindrance in the system results in the increase in rate of the reaction. In all other cases, we have seen that steric hindrance can decrease the rate of the reaction, but for IBX, due to the intermediate stereochemistry, if there is steric hindrance, it can favor the reaction rate. Next question: the major product that form in the following reaction. So here, what we are doing is this alcohol is there. Firstly, treating with two equivalents of IBX, 65 degrees Celsius. In second step with methyl lithium. Third step is hydrolysis. Fourth step is PCC, oxidation, and then the last step is this Gilman reagent addition. So what will be the major product here, and what is happening in each of the steps? It would be better if any of you can answer this.
Option number 3.
Yeah, can you tell me what is happening in each of the steps?
IBX formed formation cycloheptane.
Cyclo, uh,
Cycloheptane.
Like what IBX will do here. Okay, I will show. So this is happening as we have told earlier. IBX can be used to form cycloheptanone. So this alcohol will be oxidized into this ketone by the first equivalent of IBX. Then the second alcohol will convert that corresponding ketone into alpha beta unsaturated ketone. So IBX can be used for the conversion of alcohols into ketones. Ketones and further alpha beta unsaturated ketones. Then we are using this methyl lithium and then hydrolysis. So 1 2 attack of this methyl group is taking place over this ketone. This Me minus will attack over this. So this Me minus will attack over this sender. This will go over here and it will be coordinated with lithium. Then in hydrolysis, this will get hydrolyzed and we will get OH and Me group. Then further, what PCC will do? So this is an allylic alcohol. So PCC will help in the oxidative transposition of allylic alcohol. So that also mechanism we have seen. Like this oxygen will attack over this position. This will migrate to here and this will break. It's an in reaction type of reaction, so that will give this transposition product. Then Gilman reagent is being used, that will result in 1,4 addition. 1,2 addition will not take place, 1,4 addition will take place. This allyl group will attack over this fourth position of this double bond. So we will be getting this product. So two equivalents of IBX will give cycloheptanone. Methyl lithium adds to ketone followed by neutralization will give this allylic tertiary alcohol, which will undergo this oxidative transposition, that is Mignodobin rearrangement to form this enone. Then Michael addition, that is 1,4 addition with this allyl cuprate leads to the final product. So the correct answer is option 3. Is it clear? Any doubt in any of the steps?
Nothing.
Yeah. Now the third question is the major product that will form in the following reaction with one equivalent of the reagent. So here we are using two equivalents of this silver benzoate iodine benzene. In the second step, this KOH and water. So just now we have seen this, which will be the major product here. Any idea which will be the major product? So this is an example for Provost reaction. So as we can see here are these two double bonds, but this is more sterically hindered because of the presence of this methyl group. So this will be lesser reactive and it will not participate in the reaction. Only this will participate in the reaction. And what is happening? Firstly, this idonium ion will form. Then benzoate will attack from the opposite side, opening the idonium ion. Then this intermediate will be forming. Second benzoate will attack because water is not used in the first step. Here we can see in this no water is there, only silver benzoate, iodine and benzene. This water is for hydrolysis. So if water is used at this stage, then only water molecule will attack instead of the second benzoate. Here second benzoate attacking and forming this dibenzoate. Then hydrolysis using KOH and water will give the corresponding antidiol. So the correct answer would be option 1. So in this one, cis-diol is forming, but no water is there. In this one, cis-diol, but this alkene is reacting, but that is sterically not accessible. And in the last product, antidiol is forming, but again this alkene is reacting. That is also not possible. So the only option is answer 1. Option 1 answer. Option 1 is the answer. Is it clear? Okay. Next question, the major product formed in the following reaction. So here in the first step, this compound is treated with SeO2 in tertiary butanol. In the second step with lithium hydroxide. Third step, silver carbonate, silicate and benzene. Fourth step, lithium hydroxide again. And last step, hydrolysis with water. So which will be the major product here? Any idea? Can any of you answer? Okay, so here what will happen? Firstly, with this selenium dioxide, this yeah. So with selenium dioxide, this hydrolysis of this acetate group is also taking, no, that is not with the selenium dioxide. So first step is selenium dioxide. In that condition, what is happening? We know allylic oxidation will take place with selenium dioxide. So this allylic alcohol will be oxidized into the corresponding. What is the substrate? Okay, sorry. So they have directly given the first answer. So in the first step with SCO2 and tertiary butanol, allylic oxidation will take place. So allylic oxidation means at this position hydroxyl group will come. That is happening in the first step. Then in the second step, lithium hydroxide will hydrolyze this ester and convert into the corresponding hydroxyl group. So here also OH, here also OH. That will be happening in this first two steps. So that is this product. Then the silver carbonate, what it will doing? Allylic alcohol is also there. Primary alcohol is also there. This will oxidize selectively this allylic alcohol to give this aldehyde. Then this aldehyde, what will happen? This hydroxyl group, oxygen lone pairs can attack this carbonyl carbon center, forming this lactol. Then again, this lactol can be oxidized into further this lactone to give this product. So this we have already seen. Like one application of this Peterson's reagent is that if diol is there in a system, it will be converted into the lactol and then lactone by this Peterson's reagent. Then again, now lactone is basically ester, so this lithium hydroxide will uh, hydrolyze the ester, so this will cleave and that will be, here also OH will come and here proton will come, which will give this compound carboxylic acid over here and hydroxyl group over here. So that is the correct answer will be option 4. First, allylic oxidation, LiOH will hydrolyze the ester. Silver carbonate will convert this allylic alcohol into the corresponding aldehyde. Lactol formation, lactol to lactone oxidation, lactone hydrolysis and then neutralization will give this product 4. The next question. Sometimes in the oxidative cleavage of olefins with ruthenium tetroxides that leads to carboxylic acid, the reaction proceeds slowly and remains incomplete due to the formation of low valent ruthenium carboxylate. Starting olefin reacts with carboxylic acid to form addition product. Pi complexation of olefin with carboxylic acid reduces their reactivity. Carboxylic acid forms intermolecular hydrogen bonding with ruthenium tetroxide, reducing its reactivity. So this also we have seen now. So if the carboxylic acid, um yeah, oxidative cleavage of olefins with ruthenium tetroxide that leads to carboxylic acid, reaction proceeds slowly and remains incomplete due to the formation of this kind of intermediate, which is low valent ruthenium complex, which will suppress the further reaction. So the correct answer would be option 1. Next question. Major product that form in the following reaction sequence. So this compound is treated with firstly ruthenium chloride, NaO4, acetonitrile, CCl4, water. Just same example we have seen today. And in the second step with this diisomethane, what will be the product? So here, as we know, ruthenium tetroxide will form by the combination of ruthenium chloride and NaIO4 that will be converting. As we said earlier, this phenyl ring is having double bonds, so that will be cleaved under this condition, and we are using acetonitrile also, so we will be getting the corresponding carboxylic acid over this position. Then carboxylic acid will react with this diisomethane to form this compound. So this is used for the esterification reaction. Carboxylic acid will be converted into corresponding ester, methyl ester. using diazomethane. So the correct answer would be option 3. Now the next question, major product that will form in the following reaction. Again, same reaction which we have seen. Firstly, ruthenium chloride NaO4, acetonitrile CCl4 water. Then in the second step, LDA, phenyl selenium chloride. Third step, LD and methyl iodide. Fourth step, H2O2, and last is warm. So answer is already visible here. Try to think how we can get this with all these reagents.
Option number 2.
Yeah, can you explain?
Ruthenium tetroxide convert cyclic ether.
Cyclic ether into lactone, right?
Yeah.
Then second step, what is happening?
Second step.
What LDA and phenyl selenium chloride will do? This reaction we have seen in first week or second week lecture.
Yes.
Like first LDA will abstract proton, phenyl selenium will attack over there. Then if we add H2O2 or MCPB, it will be oxidized into selenium oxide, and then elimination will take place. You remember that reaction? Then double bond will be forming. Same with sulfur also is possible, and the selenium also possible, that kind of elimination. I will show. So what is happening? This is the first step which we know lactone is forming. Then LDA will abstract proton from this center, that will attack over this selenium. Chloride will leave to form this intermediate. Then again LDA will abstract another proton from this center, that will attack over this methyl. Iodine will leave to form this compound. Then H2O2, what it will do? It will oxidize the selenium to form this selenoxide. Then if we are heating, elimination will take place from here. This O minus will take this proton, this will go here, and this will eliminate to form this compound 2. Is it clear? First step is okay, we have discussed. Now this next step also we have discussed in the previous lectures. LDA, phenyl selenium chloride, then H2O2, then elimination. Only this is extra in that LDA methyl iodide. That is also just proton abstraction and methyl attack. It's fine. Okay, I think this is the last question. The following molecule upon reaction with Fettison's reagent allow oxidation of the hydroxyl group labeled A much faster than the hydroxyl group labeled B. So, which conformation will be favored for that? So, they are telling this is reacting faster than this one. So, for that, which conformation it would be preferable? So here, yeah. So as we can see here, this methyl group and this proton are in cis conformation. But in this first two options, as we can see, this is above, this is below, this is also above, this is below. So these two are not the answers because these are same having same stereochemistry in the starting material. So here we can see this methyl is above, this is also above the junction one. mm, yeah, this one, this is above. I think this they have given extra. This is mistake. Then here also this methyl is above, this is above. So this is the same stereochemistry as that of the product starting material. So we have to consider these two options only in this case. Now out of this, why this HA will be preferred, or out of this, when this HA will be preferred in this conformation or in this conformation? So here, between 3 and 4, tertiary butyl group in 3 is equatorially oriented, thus is a more stable and preferred conformation. But in conformation 3, hydrogen at the carbon attached to OH is axially oriented, thus less easily available for oxidation, whereas hydrogen on the carbon having OHA is equatorially oriented and thus OHA will get oxidized faster. So yeah, so they are telling this is the correct answer. So the reason is that many reasons are there. So firstly, the reason is that in this tertiary butyl group is equatorial, here the tertiary butyl group is axial. So tertiary butyl group is a very bulky group, so the axial orientation will not be preferred, so the equatorial oriented conformation will be more preferred. That is the one reason. Then the next reason is here, as we can see, the hydrogen at the carbon attached to B hydroxyl group is axially oriented. So here, this hydrogen is axially oriented. So abstracting an axial hydrogen will be difficult as compared to the abstraction of equatorial hydrogen. So in this conformation, if we see, so one reason is tertiary butyl group is equatorial here, that is favoring this. Then out of this two hydroxyl group, why OH is oxidizing faster can be explained with this conformation, because here hydrogen is axial, so this abstraction of this proton is difficult. But here hydrogen is equatorial, abstraction of this proton is more easier, so this will be reacting more faster. But in this case, this is also equatorial, this is also equatorial, so both have equal probability of getting abstracted, and both of the hydroxyl group have equal probability of getting oxidized. So we cannot explain the fact that this hydroxyl group or this hydroxyl group is reacting faster in this starting material than this hydroxyl group. With this conformation, we cannot explain that. And one reason is tertiary butyl group, then both are equatorial hydrogen, so there is no particular selectivity. But here this is equatorial, so selectivity is more for this one, and this is a stable conformation due to the position of tertiary butyl group in the equatorial position. Is it clear? I hope it's clear. If you have doubt, you can ask, I will explain again. So we will conclude with this today. The next tutorial session will be tomorrow, same time, 5 o'clock. Then we will discuss the week 4 lecture contents as well as some more problems. I hope everything is clear. If any doubts, you can ask today or tomorrow. So we will wind up today's session. Thank you for joining. Thank you.
Thank you, ma'am. You explained very well.
Okay, if you have any doubt, let me know.
No doubt.
Yeah, thank you.
Thank you. Welcome.
So you can leave that. We will see tomorrow.